Hello there, this is Travis Young with NC Software Solutions. This is an online demonstration of NC Transform, the most advanced adaptive machining solution on the market. Today we're going to use NXCam and Vericut to demonstrate the process of setting up and running an adaptive machining solution using NC Transform or NCT, and to highlight some of the capabilities of the product. Here we have a sample part in NX. It's a large, freeform part surface, about 8 feet long and about 4 feet wide. The finished model contains a couple of contoured pads that blend into the existing part surface, a cutout with a chamfered edge, and a number of countersunk holes scattered throughout the part surface. The stock model contains 2 tooling holes to locate the part surface on the machine, as well as some excess material on the pads and around the periphery of the part. As you can imagine, a part like this would be very challenging to manufacture for a number of reasons. First of all, the setup on the machine would normally require a very expensive precision fixture and a highly skilled operator. To make matters worse, the actual part surface would likely vary significantly from part to part, making it very difficult to hold tight tolerances on the pad thickness, countersink depth, and chamfer size. However, with the benefit of an adaptive machining solution using NCT, this process becomes incredibly simple. Fixture costs are drastically reduced, first-time quality is significantly increased, and machine operators now just need to load the part and let the process run. In addition, the capabilities of your shop will take a leap forward, allowing you to tackle more challenging processes with greater confidence. To set up a part like this in NCT, we start out with our nominal cut paths. Here in NX, you can see that we've got a series of cut paths. The first thing we do is finish the top of each of the pad surfaces using a kellering operation with an 1.5 inch ball end mill. Then we use a 1/4 inch ball end mill to blend in that pad surface with the existing contoured surface. We do the same thing for the second pad. Then we drill the holes using a 1/4 inch drill. We countersink the holes using a 100-degree countersink, roughing the pocket out with a 1 inch end mill, trimming the same pocket with the same tool using a 5-axis operation. And we trim the profile of the part, and then we come in with a 45-degree chamfer mill to apply the chamfer to the cutout. Those are our nominal cut paths. The next step in our adaptive machining process is to create a simple probe program to locate the part on the machine. We do this using something called a global Orient. The first thing we do in this example is we're going to use the 2 tooling holes to locate the part surface. And to do that, we simply probe 4 points in each of the holes. And then we need to locate the rest of the part surface as well. And we do that using a minimum of 3 points on the part surface. We could use as many points as we want. For this demo, we chose to keep it simple and just probe 3 points. That will accurately locate the part on the machine. The next thing that we do is apply what we call a local orient, which is simply applied. It's an orient that's applied to a specific area in the cut program. And we're going to use several features in this example. The first is something called a virtual plane. We probe around the periphery of the pad, and we can use a minimum of 3 points. We can use as many points around the outside of that pad, and that will adjust that pad surface to match the actual location of the part surface on the machine. We do the same thing for pad 2, and then we're going to use something called an adaptive spline for the cutout. And in that, all we need to do is probe about 1 to 2 inches around the periphery of the cutout, turn that on, and allow NCT to adapt that cut path to the contour of the part. Lastly, we're going to use something called adaptive points in order to control the depth of the countersinks. And here you can see all we're doing is probing a single point next to each of the hole locations. And then when in the cut program, when we enable this local orient, it will adapt the countersink depth to match the location of the contoured surface. All we have left to do here is to add some keywords into our cut program. And you may have noticed in our local Orient probe program, there's a special naming convention in our operations. We use these keywords, which is what NCT uses to apply local orients to the program. The keyword in this case is NCT-V plane, followed by the name of the orient, pad 1, pad 2, and then we have two other keywords, NCT-A spline and NCT-A points. Those are triggers for NCT to create that feature type, followed by the name of the feature. So the only thing left to do is to turn those features on and off in our cut program. And to save some time, we've added those in here already. We'll just apply them to the cut program by moving them down here. First, we use a keyword called local orient, NCT local orient, followed by the name of the orient we want to apply. Once we turn that on, it will be applied to all of the operations following it until we either turn it off or change to a different orient. We're going to apply pad 2 to these two operations below it. Then we're going to turn it off by using NCT local orient off. When we drill the holes, we don't need any kind of local orient because they are through holes. Then we're going to turn on the countersink orient so that the countersink depths are accurately controlled. And then we're going to go ahead and turn it off immediately following that. And lastly, we're going to use the pocket orient and apply that to the chamfer on the cutout. That's all we need to do. We're going to go ahead and post out these operations. And we're going to call the cut program, we're just going to call that cut NC. Nothing special about the file name. That'll take just a minute for it to post out. Then we'll post out our probe programs as well. This is posting to an SNK gantry style machine, 5-axis with dual rotary heads. There's our cut program. We'll post out now our probing programs. We will call the first one global.nc. Very simple probe program. It's really just moving around the part and touching part surface in different places. This will generate a probe report, which NCT will later analyze and apply to the cut program. Lastly, we'll post out our local orient probe program. We will call this local.nc. And there we go. We're done in NX. We will now close that and open up Vericut. First thing we're going to do, what we've done here is we've applied in Vericut, we've applied some offsets to our setup. So there's an error built into the setup, and we have a nominal cut program. We're going to go ahead and run that right now, do an auto diff on that program, and show how much excess and gouging there is in the part. The first thing it's going to do is come in with that 1.5" end mill, color the top surface of that pad, and we'll speed this up a little bit. When it's done with that, it's going to go and grab the 1/4" ball end mill and blend that surface in with the existing contour. Back to the 1.5" ball end mill. We'll finish the top surface of the second pad. Then using the same 1/4" ball end mill, we'll come in and finish the outside of that, blend it in with the existing part surface. Next, we're going to drill the holes using that 1/4" drill. This is a 5-axis drilling operation, which NCT handles just fine. And when that's done, it's going to grab the 100-degree countersink and countersink all of those holes. And using a 1" end mill, we'll hog out that pocket. Then we'll finish the same pocket and then finish the periphery of the part as well. Again, a full 5-axis operation. NCT handles it just fine. And then that went really quick, it came in here and machined the chamfer on the cutout. We'll do an auto diff on that, and we'll see how much deviation and gouging, excess and gouging we have on that part. Switch over to our workpiece view, and we can see right here, just based on the colors, we've got a significant amount of gouging and excess all around the part. This process would result in a massive amount of rework or submittal to a customer, or in the worst case, it would be scrap, all of which we want to avoid. So we can see we've got a gouging on this edge of the part. On our pads, we can measure the distance on those, and we can see we've got 80 thousandths, almost 90 thousandths on excess on the top of that pad. And if we look at down here at our cutout, we can see we've got our chamfer is all over the place. And if we look at our first pad, we can measure the distance on that, and we can see we've got 200 thousandths excess on that pad. Now what we'll do is set this process up in NCT. It's very simple to do using our process editor. This is the user interface that a programmer or an engineer would use to set up the process in NCT. All we need to do is click Process, New. So we'll bring up our process editor. We'll give it a name. In this case, we'll call it Demo. And as a description, we'll call this a Freeform part surface. We can add a setup sheet and a tool sheet here if we'd like. Let's add a picture to make it easy for the operators. There's our picture of the process. Now we're going to insert a manual input. This allows us to make the operators enter a serial number or other piece of data. So we'll call this, let's call this manual input, and the title is enter serial number. And then we're going to insert what we call a global orient, which will be applied to the entire program. This will correctly and accurately locate the part on the machine. All we need to do here is click the machine definition. In this case, it's the S&K 5-axis gantry. We will select the probe program, which we call global.nc. And then we'll change our datum type. In this example, we can do a primary, secondary, tertiary. We can do a 3 tooling ball setup if we want, or we can click a cloud of points. In this example, we'll do a cloud of points, which will do a best fit of all the points that we feed to it. Next, we will insert, let's delete this. Next, we will insert a local orient. In the local orient, we just need to select our machine name again, browse for our local orient probe program we generated. We can set a tolerance on this, a maximum local offset. Let's increase that to 0.25. Oops, 0.25. And then we've got several feature types that we can select from. In this case, we're using one called Adaptive Spline. We're going to rename this to match the keywords in our program. We use the keywords NCT-A-Spline. We're going to rename this one. This is Adaptive Points we use for the countersink. We'll call this one NCT-A Points. And then we have Virtual Plane. And we're going to rename this keyword as well to match what we used. We used NCT-V plane. Last thing, we need to add our NC program. Select the machine definition we're going to use, and then the NC program is cut.nc. We'll save this in a predetermined location so that it's available to run in the shop. We'll call this Freeform. Save that file, and it is immediately available for the operators to run. We'll go ahead and close this. We'll open up the operator interface. We're going to head down to the machine and run this part at the machine. In this case, we're going to do that in Vericat. This window here is our operator interface. This is what the operators will see. We can see that our process that we just defined already appears here. All we need to do for the operators, they would be presented with a list of operations they can select from for that machine. In this case, they only have the one that we just created. This is the demo freeform part surface. We'll select that. It brings us to a preview page where if we had a setup sheet and a tool sheet, it would appear here. And we have a picture of our process. All we need to do is click Start, and that will immediately begin the adaptive process. It will upload a probe program to the machine as soon as we enter in the part serial number. There's our serial number. Click OK. We'll upload that program to the machine. We'll go ahead and put this down in the corner, and we will run this in Vericat. To speed things up just a little bit, we're going to turn off our cut stock while we're probing the part. And then we'll hit cycle start at the machine. Let's do that again. It ran through really quickly. Over here on the left-hand side, we can see that there is the live probe data as it's coming down through the machine. We'll slow this down, run through it, probe the part, the 2 tooling balls, and then 3 points on the part surface. That data is then automatically fed back in NCT. That data will be analyzed. A second program will be uploaded with a transformation in it, which will validate the transformation that was calculated. We'll go ahead and run that. It will probe the same surfaces as before, the 2 tooling holes, and 3 points on the part surface. We can see that now our probe data has gone down to nominal. Maximum deviation in this case, it looks like, is about 2/10,000ths of an inch. That data is fed back automatically into NCT. And if it's successful, it will then upload our local Orient probe program, which will adjust for the pad locations, the chamfer, and the countersink depths. It's probing around the cutout. Now it's probing for the countersink depths. That data is fed back into NCT. We can see there's significant amount of deviation in that probe results. We have on the order of 100,000ths around the part. NCT will pick up that data, analyze it, and if everything looks okay, our tolerance, everything is within tolerance, it will generate a transformed cut program and upload that to the machine and allow the machine to continue with the operation. So we can see that our translation values and rotation values, they're displayed here. We can compare those to what we had in Vericat and make sure that's a match. We had 40, 80, minus 40, 70 thousandths of a rotation in X, Y, and Z. And we can see that those values match almost perfectly. There's a little bit of error because of the fact that Vericat uses STL files. And so there will be a little bit of error involved in that, even when we run it in Vericat. Now the only thing left to do is to run our transformed cut program. And to do that, we'll go ahead and turn off this special probing stock. We'll turn our stock model back on. And we'll run that cut program. Then we'll do an auto diff to ensure that everything went smoothly and as planned. We'll speed this up a little bit, color the top surface of those pads. And then when that's done, we'll use our 1/4" ball end mill to blend in that pad surface with the existing contour. We will then do the same thing for the second pad, color the top surface using the 1.5" ball end mill. Blend that in with the 1/4" ball end mill to the existing contour. We'll drill the holes all the way around the part using a 1/4" drill. Follow that up with the countersink, a 100-degree countersink. Mill out the cutout, and then finish that cutout with the same tool. Finish the periphery of the part. Again, a full 5-axis operation. And then lastly will be the chamfer tool to cut the chamfer around the pocket. We'll perform now an auto diff on this. And if everything went well, if we set everything up correctly, we will see nothing but white on the part, indicating that the part surfaces, part location and part surfaces were transformed correctly. Switch over to our workpiece view, and there we go. Nothing but white all the way around the periphery of the part. Inside of our cutout, we can see that our chamfer is now a perfectly sized chamfer. Just so you know, the auto diff tolerance was set to 0.003 of an inch. So we know that if there's any deviation, it's going to be well below 0.003 of an inch. We can see that that is the case all the way around the periphery of the part. We'll check our pad surfaces. And our pad surfaces, they're going to have, we can see the top surface of the pad is perfect. The contour around the outside, the blending is off just a little bit, just a hair, because of the way that we set up our operation in NX. But we can see that the correct transformation was applied to it because the top surface of that pad is spot on. Then we can see our countersink depths are drilled to the correct depth. And we can see that the periphery of the part, there is no excess and no gouging on any side of this part. As you can see, setting up and running an adaptive machining process using NCT is incredibly simple. All of this is made possible by taking all of that complexity and sophistication of a process like this and letting the software do all the heavy lifting. That concludes our demo for the day. Thank you for allowing all of us at NCSS to be a small part of your success and for taking the time to watch this live demo of NC Transform.